Rational exponents, 7-4. Okay, we're going to do this in two sections. 1, 2, 3 is on this first one, and then 4 and 5 will be on the next one. Even though, as you can see, it all follows, or I'm sorry, it all falls under the same learning objective to simplify expressions with rational exponents. Okay, so let's go on. Example 1, simplifying expressions with rational exponents. First and foremost, a rational exponent is just a fraction. That's all it is, a fractional exponent. Okay. Um, Forgot that those did not come with the little fraction bars. We'll pretend that they are there. I'll draw them in before we get started. Okay, so looking at A, we have 64. Now, the top, the numerator, represents your power of the base. So power of the base. The denominator represents the root of the base. So this is going to be 64 to the first power, but then we take the cubic root. So the cubic root of 64 to the first power. Let's go over here and look at this one. 5 is the base, 1 is the power, 3 is the root. So that would be cubic root of 5 to the first power. Cubic root of 25 to the first power. Square root of 7 to the first power. All right, we're also going to show you how to do, to write these as radicals. Okay, so this is going to be 64 to the first power, and then that's the cubic root. There we go. And hopefully by now you know that the cubic root of 64 is just 4. Coming down here to part B, we have 7 to the 1/2, so that's the square root of 7 to the first power times the square root of 7 to the first power. Well, square root of 7 times the square root of 7 is the square root of 49. The square root of 49 is just 7. Up here for C, we have cubic root of 5 to the first. So we have cubic root, sorry about that, 5, and then to the first, that's where that little 1 comes from, times cubic root, the denominator, of 25 to the first. Okay, these are both cubic roots, so that means we can multiply the radicands, the stuff underneath the radical. 5 times 25 is 125, and this is the cubic root of 125. And again, hopefully you guys know this one by heart, that it is 5. All right, guys, let's go ahead and take a look at example 2. Had a slight issue, so I cropped a little bit. With example 2, very similar to what we just did with example 1. However, with example 1, you can see that we have this decimal exponent, and we need to convert that from a decimal to a fraction before we can simplify it. So let's go ahead and take a look at the ones that we're going to work on. All right, so A, write the exponential expressions x to the 2/7 and y to the -0.4 in radical form. All right, well, easy peasy, because we've already talked about that, and we said that the numerator is always going to be the power of the base. Sorry about the handwriting, I know it's atrocious. The denominator is always the root of the base. Okay, so in this case, we have x to the 2/7. So this is the power, this is the root. So this would be the 7th root of x squared. And that's it, you're done, right? Now, the second one over here is a little bit more challenging because of this decimal, right? So we need to convert that decimal to a fraction before we can write it in radical form. So negative 0.4. I think the easiest thing to do is to identify what place value is your number ending in. And in this case, obviously the 4 is in the tenths. That's tenths with THS at the end, in the tenths place. So therefore we can rewrite this as negative 4 over 10 because we're in the tenths column. This simplifies to negative 2 fifths. So y to negative 0.4 is equivalent to y to the negative 2 fifths. Now, if you remember, a negative exponent tells you to flip the base. That is what its purpose is, not to do anything else. That tells you to take the reciprocal of the base, flip your base. So if I flip my base, right now we have y, or y over 1. To flip it to take the reciprocal is 1 over y, and we keep the same form of the exponent, except now instead of it being negative, it's going to be positive. So then we have 1 over y to the 2 fifths. This is your root, this is your power. So this gives us 1 over fifth root of y squared. Now, this does go against the rule of having a radical in the denominator, but it's okay because we are just writing this in radical form. That is the purpose. This is not proper, so if we were in an advanced math class and we were answering this question on a test, well, this question in particular, you would still leave it like it is because that's what it's asking for. But if we were working a problem out and it had a radical in the denominator, you would rationalize it. Okay, so now taking a look at B, write the radical expressions, fourth root of C to the third, and cubic root of B raised to the fifth power. Okay, the first one is easy. We have fourth root, and remember up here, power is numerator, root is in the denominator. So our base is C, and the numerator is the power of the C, so that's 3. And then the denominator is the root, and so that would be 4. So this is C to the 3/4. Okay, now I write this slightly different than the textbook author, and that's okay, because it all works out the same in the end. Let me show you what this is in expanded form. So this is the cubic root of b to the fifth power. So that means that we have cube root of b 5 times, right? 1, 2, 3, 4, and 5. So cube root of b to the fifth power. Since each of these is cube root, that means they have the same root, which means we can multiply the inside stuff, the radicals, together. So therefore, this is equivalent to cube root of b to the fifth power. Okay, textbook author tends to write it like this an awful lot, whereas I tend to favor this method. Okay, so now writing this in exponential form, b is the base, numerator is the power of the base, the power of the base is 5, and the root of the base is 3. Okay, we're running low on time, so I need to get going on example 3. Hopefully this makes sense. If not, just let me know. Okay, final question that we're looking at with today's problem, the first part of it, is the word problem, real world application. The time t in hours needed to cook a pot roast that weighs p pounds can be approximated by using the equation t equals 0.89 p to the 0.6, yak 0.6, right, to the nearest hundredth of an hour. how long would it take to cook a pot roast that weighs 13 pounds? Okay, so um, let's look and see what they've got. Here is the equation, right? We want how to know how long it would take. How long? So that's the T. And we are given weighs 13 pounds. So with respect to the equation, we have T, I'm sorry, we're looking for T and we're given P. P is the 13. Okay, so now we just need to substitute everything in, and that gives us T equals 0.89, 13 raised to the 0.6. Okay, so putting this into a calculator similar to the classroom set that we use, we would have 0.89 times 13 raised, ooh, sorry about that, 0.6, hit enter. I'm going to see if I can pull up that other calculator. Okay, and so we had 0.89 times 13 raised to the power of 0.6, and that gives us 4.147. So 4.147. 4.147. To the nearest hundredth. Hundredth is right here, so that's going to be 4.15 hours. All right, hopefully that makes sense. Hopefully we're all good, and I'm going to go ahead and upload this so I can get on the second one.